In the previous lecture, we saw how a charged particle can be scattered off by a magnetic inhomogeneity. And in a plasma, these magnetic inhomogeneities are going to be associated with our turbulent structures, and as the turbulent structures are moving around, they are going to scatter off the particle. So in this lecture, we will consider the motion of the turbulent structure, that is the motion of the magnetic mirror, along with the momentum or energy of the particle, and we will see once after scattering how this energy transfer is going to happen between the scatterer and the charged particle. To keep our description simple, we are not going to assume this is lost cone effect. Rather, we will consider all velocities. What we are considering is going to be out of lost cone. So the particle cannot punch through the mirror. It will always get scattered. And further, to simplify, we will consider this scatterer, which is associated with the turbulent structure, is very massive compared to the charged particle which is being scattered off. So the center of mass of the system will lie on the scatterer itself. So the frame of scatterer will be the center of CM frame of the whole system. So here we have drawn the frame of references. Let us represent this frame K as a lab frame, and this K prime frame is the one which is attached with the scatterer, which is moving at a velocity v along the x direction. And this blue point is the charged particle of consideration, which has an energy E and a momentum P with respect to the lab frame, and which gets scattered off by the scatterer sitting in the K prime frame. So with this is the frame of the system of frames which are going to deal with it. So now we wanted to get how this energy and momentum are going to be measured in the K prime frame. So well, we all know the Lorentz transformation. A simple Lorentz transformation is how the coordinates are being transferred between the K prime frame and K frame. That is very well known to everyone. What we have is, we have the x of the K frame will be equal to x prime plus vt prime divided by root of 1 minus v square by c square. So this is nothing but we write your gamma equal to 1 by root of 1 minus v square by c square. Therefore, your x equal to gamma times x prime plus vt prime. And similarly, we have the time is equal to gamma t prime plus v by c square of x prime. So in fact, to transfer this momentum and energy also, all what you have to remember is only these two transfers. Most of the cases, Lorentz transformations, if you know these two relations, you can in fact get all the Lorentz transformations. So all the physical quantities. So for example, if you take the derivative of dx by dt, you know dx and dt, explain this one. So when you take a derivative of it, it gives how the velocity is going to be transformed between the two frames. Or if you put that after velocity transformation, if you substitute that v as c and represent all your x component of v in terms of cos theta or sin theta, whatever you want, that's going to give you the transformation of angles, or what you call as the aberration of angle. So anyway, we will not go into those things, but what we want to know is, now we have this says how my x and t are going to be connected between these two frames. But what we want is how my energy and momentum are being connected between these two frames. So if in the 4-vector form, this t corresponds to the 0th component and the x corresponds to the vector component, x, y, z correspond to the vector component. So similarly, in the 4-momentum representation, E corresponds to the 0th component and t corresponds to the vector component. So we can actually see the E corresponds to time and the P corresponds to the vector. So it is simply, I can replace these guys with a corresponding component and then use the factor of C. What are the factor of C required to match the equation dimensionally? So this is a simple way to get the transformation of different physical quantities. So then I can always take this equation. So x I'm going to replace by P of x. So P of x is going to be gamma times P of x prime plus V into T is nothing but my energy time. So now if you see, you can see this is not P of, this is to have dimensionally match these two, I have to divide by the C square. So now dimensionally it matches. So this is the one relation which is going to relate how the momentum is related between these two frames. And similarly, in the place of t, I can have E into gamma, that will be E prime plus V by C square, and X prime, that will be your P of X prime. Okay, now you can see this should be multiplied by C square to get the dimension of energy. So this is going to basically become something like V by Px prime. So this is the quantity which is going to relate between which is going to give the relation between the momentum and the energy of the particle in the K prime frame and the K frame. So let us note it down here. So what we are having is your energy E is given by gamma times E prime plus V P of X prime, and your momentum P of X is equal to gamma times P of X prime plus V by C square of epsilon prime. Sorry, this is prime here. Yeah. And your gamma is nothing but 1 by root of 1 minus V square by C square. Well, to get the converse, that means how E prime is related with respect to E, all we have to do is, you can always do find it out from calculating, but simple. This is simple. When you sit here, the velocity of K is going to be opposite. So just change the sign of the V. That gives you how the E prime is going to be related to E. So that gives you, so E prime is going to be gamma times E. Now the velocity is reversed, so it's going to be minus V Px, and your Px prime will be equal to gamma times Px minus V by C square of E. Right. So this quantity, so let me call it as 1 and 2. This says what is the energy and the momentum of the particle measured from the K prime frame. So now we said the K prime frame is the center of mass frame. So after scattering, the momentum will just change the sign. So after scattering, so there is a momentum Px after scattering is going to be minus Px of, sorry, this is a prime. And the energy has to be conserved in scattering because the elastic collision we are doing. So therefore, Es prime should be equal to E prime. So now we have considered the collision in the K prime frame. Now let us jump back to the K frame and see how these quantities are going to be, how the scattered momentum and the scattered quantity are going to be related to the going to be seen in the K frame. So that's from the same equation. So your scattered energy epsilon S is going to be gamma times scattered energy in the K prime frame plus V Px scattered energy in the K prime frame. So now let us substitute Es prime is nothing but my E prime, and this Px prime should be equal to this one. So this is going to be gamma times E prime minus V Px prime, because the sign changes. Fine. So now we are going to substitute for the E prime and Px prime. Let me substitute from here. So what you are going to get, your epsilon S is equal to gamma times, so E prime, so there is our 2 gamma, so it becomes gamma square. So this is going to become epsilon minus V P of X minus V into P of X is P of X minus V by C square into epsilon. So eventually we got the energy after scattering in terms of all the quantities which is measured in the K frame itself. Now we don't have anything in the K frame, so we got the required, all we wanted is what is E is the initial energy, the scattered energy in the K frame. That's what we wanted to know it. So we got all the relations. Now we have to just only do the mathematical jugglery. So you can see, so this is going to be gamma square epsilon, so minus V of x, so this is going to become epsilon minus 2 VPx, and then what we are going to get is this is going to become plus V squared by C square of epsilon. Fine. So now if I try to write down what is my gamma square, because we know this is a gamma square, so this is going to be divided by 1 minus V square by C square. So let us have a situation. Your V is much smaller than C. That means I'm saying that your scatter is moving mildly relativistic, so that V by C is much less than 1. So in that case, what happened? We will neglect every term which is going to be more than the second order of V by C. That means if anything is having V by C whole cube or fourth power or fifth power, we are going to neglect it. So in that case, and since it is much smaller than C, I can always express this quantity, that is 1 minus V square by C square minus 1 as approximately 1 plus V square by C square. Correct? So this is going to become into 1 plus V square by C square. So now, let us multiply it. So we are going to have, what we are going to have is, so anyway, with the 1 we will get the first term to be same, epsilon minus 2 V P of x plus V square by C square of epsilon, and then the second term comes, so that is going to be plus epsilon V square by C square, and then minus 2 V P of x V square by C square, and this is going to be the fourth order, so we can neglect it. So we are going to have this equation as, so we will have this equation as, so let us write it, epsilon s is equal to epsilon minus, this is twice, so minus, minus 2 V P of x plus twice V square by C square of epsilon minus 2 V P of x, into V square by C square. So now I can do a furthermore jugglery. We will try to express this P of x in terms of the energy. How we are going to do it? So we know your P of x is equal to gamma m V of x, where gamma, this is a small gamma f, this is the gamma of the particle, not of the frame. So if gamma of the frame is here, so gamma of the particle, and the energy E, we know that is equal to gamma mc square. So combining them both, I can always write my P of x is equal to, so gamma m is equal to epsilon by C square. Substituting here, we are going to get epsilon energy by C square into V of x. So I am going to use this P of x everywhere here. So this, then my epsilon s is going to become epsilon minus 2 V. P of x is nothing but E by epsilon by C square V of x plus 2 V square by C square epsilon. And now this quantity, if you see, P of x is going to become, there will be one C square come here. So when I put C square, so if I take C, so this V by C square and V by C that get multiplied by V by C whole to the power of third order. So obviously this is going to, we said that since from third order we are going to neglect it. So this quantity goes off, and therefore this is all we get. Okay, so now the change in the energy, that means the energy, what will be the energy after scattered and before scattering, what's the change in the energy? That will be nothing but my epsilon s minus epsilon, that I'll call, okay, let me call this delta epsilon. Delta epsilon equal to epsilon s minus epsilon, and that will be, am I missing something with the sign? No, yeah. So this is going to be 2v square by c square epsilon minus 2v epsilon by c square vx. Correct? Okay. So now let me calculate what is the fractional change in the energy after collision. That is delta epsilon by epsilon. That is going to be, I take the epsilon commonly outside. In fact, I can take your 2v by c square also commonly outside, 2v by c square, and that's going to be 1v minus v by c square 2 minus v of x. So this equation gives us what is the fractional change in the energy of the particle due to the collision. So this is what an expression we require. So we will remove all this and we will write down this equation. So the fractional change delta epsilon by epsilon will be equal to 2v by c square into v minus vx. So vx is the x component of the particle, the x component velocity of the particle that is being scattered off. So here, okay, let us take the same picture. If this is the velocity vector, so then the x component will be along this side. So if I take this angle as theta, then the x component goes in the negative of x. So this is going to be minus v cos theta. Therefore, your vx is going to be, this is a head-on collision because the particle is going to go coming and hitting the scatterer. So it's a head-on collision approximation, right? So in a head-on collision, so vx is going to be minus v cos theta. So when I substitute back here, therefore your delta epsilon by epsilon equal to 2v by c square v plus v cos theta. You can see clearly this is a positive quantity. So delta E is going to be positive. So therefore there is going to be gain in the energy. So all the head-on collision, the particle is going to eventually gain the energy due to the head-on collision. So now let us take the another case. Suppose, let me remove this one. Suppose if the particle is along this direction. So then this will be the x component which is in the positive. So this is going to be the follow-on collision. So and then if I call this as theta, so this will be equal to your v of x. Under this case, this is for your head-on collision. So now in the case of follow-on collision, so your v of x will be v cos theta. So now v of x is equal to v cos theta. Therefore delta epsilon by epsilon is equal to, you can call it either E or epsilon, whatever, v by c square v minus v cos theta. And now if you see this relation, v will be generally larger than v, because see, for the scatter velocities, this is massive scatter, this is not going to be that the charge particle is going to have a larger velocity than the scatterer, because massive scatter. It's okay in a simple day-to-day life. You want to see, if you're playing a table tennis, obviously when you hit the ball, with the bat, the ball is going to have more velocity than the bat. So naturally this v is going to be much higher than v, and for a small angle theta, this quantity is going to be negative. So since it's going to be negative, this is going to have a loss of energy. So the particle lose energy in the follow-on collision, whereas the particle gain energy in the head-on collision. So this is basically follow-on collision. Okay, so now let us come to, so this is what the description. So in this description, so we are consider the scatterer is going to move as well as the particle is having energy and momentum. How is the transfer of energy happens during this collision is given by this equation. Now let us consider the case. Suppose if there are scatterers which are moving randomly all over, and the particles are going to are also going to move randomly. So there's all possible collisions. Still, what you will see is the probability for the head-on collision will be always more than the follow-on collision. So there will be always a gain of particle energy. Well, why do we say that probability for a head-on collision is larger than the probability for a follow-on collision? Well, if you're traveling in a bus or a car, you will see more of the vehicles are coming from the front than the one which is overtaking you. So naturally, as the scatterers are moving, it's going to see more particles coming and hitting them on the head-on than the one which is going to overtake them. So naturally, so the probability is going to be higher for the head-on collision. So therefore, there will be a net gain in the particle energy. And this process in which a stochastically moving the scatterers and the particle when they move, so eventually the energy is going to be transferred from the scatterer to the particle and the particle gain energy. So this type of acceleration was first proposed by Fermi and was called as your Fermi acceleration. In the next lecture, so we are seeing so the two cases how the energy is going to change when you are when there's a head-on collision and a follow-on collision. What will be the change? So the next lecture we will try to derive the probability for the head-on collision. So in the randomly moving scatterers and the particle, we will try to derive the probability for the head-on collision. Once if I know the probability for the head-on collision, then always I can find out what is the mean energy gain, the gain by the particle by remaining in the regime of stochastically moving magnetic mirrors. Thank you.